All right, this is going to look at a practice problem on different wave properties, and I have two waves drawn here for a comparison. You have to imagine, just squint your eyes maybe a little bit, that they're actually drawn well and beautifully represented periodically in space. And so I have my dimensions of meters along the vertical axis, meters along the horizontal, meters along the vertical axis, in terms of representing the physical properties of these waves. All right, so the first question asks us to rank the wavelength. Which of these two waves, the blue wave or the pink wave, I don't know if you can distinguish the colors on the light board, but the two waves have a longer wavelength. And remember, wavelength is that spatial representation of the wave. How long is the wave? And so if I look at the first wave, I only look at a wavelength through a complete cycle. So I'm going to start at the 0 point, and I'm going to go up, down, and back to the start point again. That's one cycle, and I see that blue wave is sort of in this dimension here. To do it with the pink wave, I go up, down, and back, and I see I have to move my arm over here to get that full cycle. So the longer I move my arm, the longer the wavelength. The pink wave is greater than the blue wave. And if we can't see those, I'll just tag them. So here's pink, and here's blue. All right. The second part reads, which wave, if either, has the higher frequency? So when we look at this, frequency is the number of cycles per second, remember. And it really has to do with how many cycles an object would have in a given second. So how tight those wavelengths are to one another, right? So how squished. The more squished we bring those wavelengths together, the higher the frequency. And so we can see that the blue wave has a higher frequency. So the frequency of the blue wave is greater than the frequency of the pink wave. Now we learned, does that make sense from what we learned in a mathematical standpoint? Remember that we learned that the velocity, the wave speed, remember, was related to the wavelength times the frequency. So if I increase my frequency for a wave, we're going to find what wave speed, we're going to dive a little deeper into wave speed. Let's imagine these waves are traveling along together. If I increase my frequency, I decrease my wavelength. And so visually it looks like they're going up and down faster, more frequency, and their wavelengths are shorter. So it also makes sense from a mathematical perspective, assuming they're traveling at the same wave speed. And I encourage you to check out that wave speed to see if that assumption makes sense. It does, I'll tell you right now, it does make sense. But it's easy to recognize that if we consider these traveling along together. All right, so the frequency of the blue is greater than the frequency of the pink wave. And that says, from this data, can we determine the wavelength? Well, yeah, remember, the wavelength is simply how long that wave is cycle to cycle. And I know I did the wavelength comparison from the start, but visually I think it's a little easier if we go from a peak to a peak or a trough to a trough. So there's the blue guy, and it goes from 1/2 a meter to 2.5 meters, or we can see from 0 to 2. So the wavelength of our blue wave is equal to 2 meters. And what about the pink wave? Well, it starts and it goes back to start for 4 meters. So we can read right off the graph our wavelength of these waves. And then the final question asks us to calculate the frequency based on our wave speed, generic wave speed calculation. And again, you were given that in this sort of introduction. We're going to work on it much more intently in when we talk about how we use that information. But if we calculate the wave speed for each wave, if we want to know what the frequency is, if we calculate the frequency for each wave, it tells us that the wave speed is equal to 12 meters per second. So that means the speed of the blue wave is equal to 12 meters per second. I'm not going to put the 12 in there. Sorry, the label, just to make it less messy. That equals the wavelength, just as a reminder, the wavelength of 2 times the frequency. So we know that our frequency is equal to 6 hertz. And for the pink wave, also 12 meters per second, that is our 4 times our frequency. So we have 3 hertz frequency for the pink wave. Now, conceptually, did that match what we found before? Yeah. So we said we predicted that that frequency of the blue wave would be larger than the frequency of the pink wave, based kind of on visual inspection, just sort of how we feel about it, right? Visually inspecting, it looks like they're going up and down more often in the same space. And we also, of course, represent that in our wave speed equation. All right, using wave descriptors somewhat quickly. Now, if I were to also ask what's the amplitude of each wave, let's just add that in there. What's the amplitude of my blue wave? Well, that is represented here, which is 0.5 meters. The amplitude of the pink wave, 0.25 meters. So, little bonus info there. All right, good job.